Okay, so we're still doing synthesis of alcohols. So we've introduced alcohols, and now we're going to do the synthesis. And we just finished POGL 14, and we're going to do POGL 15. So this will probably be a short lesson going over POGL 15. POGL 15 is oxidation and reduction. And in your chapter, if you reduce carbonyl compounds, the carbonyl group, this is a way to synthesize primary and secondary alcohols. The next POGLs after POGL 15 will be reactions of alcohols. So right now we're just synthesizing alcohols. Now the reducing agents that you need to know and become familiar with are called hydride reagents. And so you have sodium borohydride, and you have lithium aluminum hydride. So let's look at sodium borohydride. You'll see it's NaBH4, and lithium aluminum hydride is Li aluminum hydride. And let's draw the Lewis structure. So if you have boron in the middle, and you have boron has 4 hydrogens, and then this is a negative charge, and then sodium is a positive charge. And let's look at that to make sure. So what's the formal charge on boron? Well, boron is what group number? Group 3. So group number 3 minus, let's do dash and dots, right? So we have 1, 2, 3, 4. So 3 minus 4, and there's no lone pair, so 0. 3 minus 4 is a -1. So that's why boron gives a -1, and then it would form a salt with the sodium. A salt is anything with a negative and positive. So this will deliver a hydride. Okay, so a hydride, what is a hydride? The IDE means it's a negative charge, so it's hydrogen with 2 electrons. Okay, that makes it a hydride. When we do acid-base chemistry, we deal with a proton, which is an H+, and that means hydrogen with no lone pairs, no electrons. Okay, so hydride is delivering basically a covalent bond. It's taking these 2 electrons, and this makes it nucleophilic. So you can see where the hydride is nucleophilic, whereas a proton is an electrophile. So even though they're both H, you can see that one's an electrophile and the other one is a nucleophile. Okay, lithium, aluminum, also it's in group 3, and it forms 4 bonds there with a negative and then a lithium positive. You can do the formal charge of a aluminum. Aluminum has group number 3 and -4 -0, so it's also a -1. Now I'm going to tell you, this is a very strong, very powerful reducing agent. In fact, and it also, if you get lithium aluminum hydride around alcohols or water, it can cause a fire. Okay, so it can be very dangerous. So you're going to have to use ether solvents like THF. Usually it's always THF. Diethyl ether is usually lower boiling, so you choose tetrahydrofuran, which is an ether solvent. It does not have a free proton, and so that is a good solvent. Sodium borohydride, you can actually use larger quantities of these in alcohol solvents. You can also, but I typically would choose an ether solvent as well. So those are the 2 reagents that you're going to choose from for reduction. These are reducing agents. Now let's talk about reduction. Okay, so reduction, let's talk about carbon. So if we go this way, we're going to oxidize carbon. Okay, and then you go this way, this is going to reduce carbon. And we care about carbon because we're organic chemists. So this is fully reduced carbon, and this is fully oxidized carbon. So here, if you take something like methane, so alkanes are fatty and they have lots of hydrogens, and you have 4 hydrogens. Well, if we remove a hydrogen here and we replace it with oxygen, okay, so when you oxidize, you're adding oxygen and you're removing hydrogen. When you reduce carbon, you're adding hydrogen. So it has 1 hydrogen, so now we can go this way and we replace that with an oxygen. Okay, so now we replace that carbon, hydrogen with an oxygen, so that's an alcohol. And it's a methyl alcohol, if you classify it. Okay, now we have another hydrogen we can remove. And so if we replace that, you now have a carbonyl. So this is formaldehyde. So you replace that now with a carbonyl. And then do we have another hydrogen? Yes, we do, because carbon's bonded to 4 things. So we can remove that and replace it with an oxygen. So now we have a carboxylic acid. And then do we have another hydrogen? We do. And we can replace that with an oxygen, which is carbon dioxide. So just exhale, and you have carbon dioxide. That is fully oxidized carbon if you take a methyl. If you have a secondary, or let's say if you have a carbon bonded to another carbon, so let's say ethane. Okay, so now we have one of the, it only has 3 hydrogens here. So if we take one of these hydrogens, we replace it with oxygen. We have our CH3. We have a primary alcohol. And then if we have another hydrogen, and we replace that with an alcohol, a carbon, we have an aldehyde. And you see that we have another hydrogen. And if we take that away and replace it with an oxygen, we're oxidizing it. Now we have a carboxylic acid. Okay, so that's fully oxidized carbon. Can we go any further? No, because that carbon does not have any more hydrogens. Now let's look if we have a carbon. It only has 2 hydrogens. Okay, so we have 1 hydrogen that we can remove and replace that with an alcohol. What is that? That carbon's bonded to 2 carbons. That's a secondary alcohol. All right, so now do we have another hydrogen we can remove? Yep. So We can replace that with a double bonded carbon-oxygen bond, and that's a ketone. Can we go any further? No. There's no carbon-hydrogen bonds left. Okay, so that's as far as we can oxidize a secondary alcohol. Okay, let's look if we take a carbon that only has one hydrogen. Here we have one hydrogen, and so we replace that with an OH. We have a tertiary alcohol. Can that oxidize any further? No, it can't go any further. So a tertiary alcohol cannot go to anything higher oxidative state than a tertiary alcohol because there's no hydrogens on the carbon to remove. So that is the theory of oxidizing a carbon, and we're going to learn what oxidation agents are. That's going to be oxidizing agents will be discussed in the reactions of alcohols next chapter. But this model is going to talk about reducing agents, so sodium borohydride, and they go this way. So we can reduce, and that means we're going on the path this way. So let's look at PG15, and this is oxidation and reduction. And so model 1 does reduction reactions. Equation A. This is equation B. This is equation C. Reducing reagents are RED, and strong reducing reagent is lithium aluminum hydride, and weak reducing reagent is sodium borohydride. So strong is lithium and weak is sodium borohydride. Now let's answer the questions. One A. The number of carbon-hydrogen bonds for equation A is, so we're reducing, okay? So the carbon-hydrogen bond here is, here it has none, and if you wanted to draw it in, you would see that you have a hydrogen, so it has increased. Equation 1. The number of carbon-hydrogen bond in equation 2 has increased. The number of carbon-hydrogen bonds in equation 3 has increased. So here we have 0 carbon-hydrogen, 0, 1, and here we have 3, 2, 1. Okay, for reduction reactions from left to right, in model 1, the number of carbon-oxygen bonds. So here we have 2 carbon-oxygen bonds. Here we have 1 carbon-oxygen bond. So that has decreased. Here we have 3 carbon-oxygen bonds. Here we have 1 carbon-oxygen bond. Here we have 0 carbon-oxygen bonds. Here we have 0 carbon-oxygen bonds. So this would be the same. So these would be decreased, that would be the same. Okay, number 3, using the above information, reduction of organic compounds can be described as an increase, so increase to the bonds of hydrogen, so increase the number of carbon-hydrogen bonds, and a decrease in the number of carbon-oxygen bonds. Number 4, consider the reduction reaction. Okay, let's look at this reaction. I like to draw them out when we're doing reactions so we can see all the bonds and see what's going on. This is where you're problem solving, folks. Just because a problem is given to you in a certain format doesn't mean you keep it in that format. Okay, so we have to draw it out in Lewis structures. If you don't remember how to do this, then you might want to go back to Pogel exercise 1. It shows you how to go from condensed formulas to Lewis structures. Okay, so let's answer questions 4A. The number of carbon-hydrogen bonds are, so we have 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. The same. The number of carbon-bromine bonds. Here we have 2 carbon-bromine. Here we have 0 carbon-bromine bonds. So it has decreased. Compare the effects of halogens to that of oxygen in a reduction reaction. Halogens are classified as the same. Okay, so it's just a more electronegative atom, so it's the same. Explain why this reaction is a reduction. It's because you're decreasing the number of bonds formed from a carbon more electronegative atom, and that's also considered a reduction. For us in our class, we're just really going to need to focus on just the the oxygen. So let's just go ahead and skip 5, and let's just go straight to 6, question 6. I think that's important, and then model 2. So question number 6, reducing reagents can be classified as strong or weak, shown in model 1. Compare the starting carbonyl compound to the product of the following reactions. So you can go ahead and answer those. So we have acids, esters, ketones, and this is going to be a very important one. I would star this, aldehydes. And this is lithium, aluminum hydride reductions. And they're showing the reactions. And you could draw these out if you need to. So here's like a ketone. So you can see the Lewis structures. And then aldehydes. And then this is the sodium borohydride reduction. So if you use this reagent, it's showing you I would just write NO or NR, no reaction. So for our purposes, I just write no reaction. I wouldn't write those. Do not write the starting material as the product for your reactions. If there's no reactions, then write NR. And then here we have an aldehyde, and you get a primary alcohol. Okay, so 6A, which carbonyls undergo reduction with lithium aluminum hydride? So if you use lithium aluminum hydride, you see that you get a carboxylic acid and it goes to a primary alcohol. An ester goes to a primary alcohol. A ketone goes to a secondary alcohol. Aldehydes go to a primary alcohol. So they all form synthesized alcohols. So these are your starting materials. With this reagent, you can get primary and secondary alcohols. So I would circle acid, ester, ketone, and aldehyde. They all get reduced and they all make alcohols. Okay, what about 6B? Which carbonyls undergo reduction with sodium borohydride? No reaction for carboxylic acids. Okay. No reaction for esters. And then your ketone gives you a secondary alcohol, the same thing. And an aldehyde will give you a primary alcohol. So this is weak, okay? So it can reduce ketones and aldehydes to secondary and primary alcohols. So ketone and aldehyde. Are any of the reducing reagents unable to reduce some carbonyl compounds? And the answer is yes. It says list those. Sodium borohydride cannot reduce acids and esters. Okay, it can't reduce those. So once everyone in your group agrees on the above reaction concepts, determine the reducing agents that accomplish the following transformations. And if we were in class, I would write this up on the board. And I would choose a group to come and fill in these reagents. So first thing I want you to do is classify what's going on. So classify your alcohols. When you're trying to solve organic chemistry reactions, you give functional groups. Okay, so this is your starting material. This is an ester and this is a ketone. Then you come over here to the product and you say this is an ester and this is a secondary alcohol. And you come here, you say this is a primary alcohol and this is a secondary alcohol. So the first one, esters, no reaction. Esters stayed. But you were able to reduce a ketone to a secondary alcohol, so that would be sodium borohydride. And this one here, you were able to reduce ester and ketone to the alcohols, so this would be lithium aluminum hydride. Now let's do the oxidizing reagent, because you're going to need to know this anyway for the next chapter. Now we're doing model 2, and this is called oxidation. So now we're going to learn some oxidation reagents, and we're going to go the other pathway. So now we're going from an alcohol, and we're going to add an oxidizing reagent. So we're going to learn some new chemical reagents. And here equation D. Here we go from a primary alcohol, and we're going to a carboxylic acid here for equation E. And here we're going from an alkane to an alkene. That's equation F. And now for our oxidizing reagents, we have strong ones, just like we had reducing reagents. And we're going to have to draw these out so you can see. Chromium. And what do all these have in common? Notice the metal has lots of oxygen. Just like our reducing reagents that delivered hydrogen, hydride, had lots of hydrogens. These reagents deliver oxygen. So they have lots of oxygen. Okay, and this is called the Swern. So these are weak. You notice so PCC, you can write PCC instead of writing all the actual reagents. I will allow you to write PCC for weak. You could also use a Swern. You could write Swern. Sometimes you might need to also recognize those reagents, oxalochloride, triethylamine, and DMSO, in case you have a multiple choice question. Strong oxidizing reagents are like the chromium and acid, or potassium permanganate, which you've seen before in organic 1. So, and notice your magnesium has lots of oxygen. Chromium's the same way. And then here, this is an acid, so you also have water present when you have acid. The difference between weak here is you have no water. This is usually done in dichloromethane. And pyridinium chlorochromate looks like this. So there's your plus, and then your chromium. And so there's the PCC, and then your Swern oxidation, oxalochloride looks like this. And that will deliver these oxygens here, but they're very dry conditions. So there's no water. So that's how you can have a weak. Now let's answer our questions. So 7. From the oxidation reactions from left to right, shown in Model 2, the number of carbon-hydrogen bonds are doing what? So let's look. Here we have 1 carbon-hydrogen bond. Here we have 0 carbon-hydrogen bond. Here we have 2 carbon-hydrogen bonds. Here we have 0 carbon-hydrogen bonds. Here we have 1, 2, 3 carbon-hydrogen bonds. Here we have 1 carbon-hydrogen bonds. So did you write decreased all the way through? They're all decreasing, and that's what makes it oxidation. Okay, number 8. For the oxidation reactions from left to right, shown in Model 2, the number of carbon-oxygen bonds. So here we have a carbon-oxygen bond, which is 1 carbon-oxygen. Here we have 2 carbon-oxygen bonds. Here we have 1 carbon-oxygen bond. Here we have 3 carbon-oxygen bond. Here we have 0 carbon-oxygen, and we have 0 carbon-oxygen. So did you write increase, increase, and then same? Using the above information, oxidation of organic compounds can be described as an increase in carbon-oxygen bond and a decrease in carbon-hydrogen bonds. Okay, I'm going to skip over 10, and we're going to go straight to question number 11. And 11 is important. I want you to put a star by 11. So oxidizing reagents can be classified as strong or weak. Compare the starting material. So this is a lot like that last problem we did. We have primary alcohol, we have secondary alcohol, we have tertiary alcohol, and we have aldehydes. Okay, so strong oxidizing reagents. So this is just giving you an example of when you take a primary alcohol, you're going to make a carboxylic acid. If you take a secondary alcohol, so I'm just going to draw a secondary such as that, an oxidizing reagent, you get a ketone. If you have a tertiary alcohol, you get no reaction. Okay, so, and then if you take an aldehyde and you put in an oxidizing reagent, you get a carboxylic acid. And then for weak oxidizing reagents, if you take a primary alcohol, you get an aldehyde. If you take a secondary alcohol, you get a ketone. Tertiary alcohol, there's no hydrogen, so you get no reaction. And an aldehyde with a weak, you get no reaction. Okay, so let's look at 11A. Strong oxidizing reagents. Okay, so we're looking at potassium permanganate, or that's a Jones reagent. You could call that Jones reagent, which is the sodium, chromium, and sulfuric acid. Okay, so Jones reagent. It will convert primary alcohols into carboxylic acids. It will convert weak oxidizing reagents will convert primary alcohols into aldehydes. That's an aldehyde because of the hydrogen. Strong oxidizing reagents will convert secondary alcohols into ketones. And what about weak oxidizing? Also ketones. So this is the same for secondary alcohols. They're the same. Okay, what about strong oxidizing reagents for aldehydes? Aldehydes go to carboxylic acids, and for weak, there's no reaction. So that's a difference. So weak will stop at the aldehyde. Okay, that's really important here. Weak oxidizing reagents will stop at the aldehyde and will not go to the carboxylic acid. Strong will go all the way to the carboxylic acid. Now let's do F. So here now we have our starting material is the diol, and once again you want to look at your starting material and decide what's your starting material functional groups, and you want to do the same thing for your products in order to problem solve. So here you have a secondary alcohol, and here you have a primary alcohol. Over here you have a ketone, and over here you have a carboxylic acid. Over here you have a ketone, and over here you have an aldehyde. Now, so if you look at the top here, what do you need? Your choices are either strong or weak. Okay, you got carboxylic acid, so you're going to need a strong oxidizing reagent because both of those go to ketone and a carboxylic acid. So you want a Jones reagent, which is basically, sometimes you might see it like this, the chromium, like that, and that's with the acid, or you have to make it with the sodium chromate plus sulfuric acid. So that's Jones, or potassium permanganate. But I kind of like the chromium, but permanganate would do the same. Okay, the next one, you have a ketone and aldehyde. So anytime you see the aldehyde, you should think, oh, weak oxidizing agent. So I'm going to use PCC. That's my favorite, which is pyridinium chlorochromate. Okay, so there's no acid or water. Or you could do SWERN. You could write SWERN, and that's basically oxalochloride, a little bit of triethylamine and DMSO, and it smells like a pig. We call it the pig reaction. All right, that concludes your problems, your models, and now you need to do the additional problems that accompany POGIL Activity 15.